Hey everyone, I hope you're doing well today. Today we're going over this calculus limits test review for Unit 1. And this video we're going to go over the multiple choice questions that we're going to have that look similar to what's going to be on the test. And then in a separate video, I'll go over the 2 free response questions that are in the review. As we're going through this multiple choice, I do want you guys to know that not all of the problems have multiple choices, but they do come from multiple choice questions. I may have just taken the multiple choice out to make you think a little bit harder and actually arrive at a correct conclusion. So let's get right into it. In number 1, we're going to be looking at x equal to 3 is the function f continuous. So we're here looking at 3 right there. We're looking at this piecewise function. So we want to think about the definition of continuity. I tried to pound it into everyone's head that the limit of f of x as x approaches 3 should be equal to the function at 3. That's what we need to confirm. And as we're doing this part right here, the left side, the limit of f of x as x approaches 3, we have 2 sides. So here's 3, here's a number line. Let me draw it right there. And if we're looking and we're approaching 3 from the left and right side, that means limit. And in a piecewise function, we have 2 different pieces. So let's figure this out. The limit of f of x as x approaches 3 from the left side, we're going to be using values less than 3, so this first function. So that's going to say to us, all right, what is 3 squared? And that gets us 9. Now as we're doing it on the right side, the limit of f of x as x approaches 3 from the right side, well, we're going to substitute 3 for values greater than 3 from that limit on the right side, and we're going to substitute 3 in for this x. So 6 times 3 minus 9, and that's going to get us 18 minus 9, which is also 9. Now this equation also satisfies f of 3 because it's also equal to. So we do want to keep that in mind. So the function and the limits all approach the same value, so we can say yes, this function is continuous at 3. That is 9, and then also that f of 3 also equals 9. Moving on to question 2, it says let g be a continuous function on the closed interval 0 to 1. Let g of 0 equal 1 and g of 1 equal 0. So let's see what that means to me. All right, so we have a function that is continuous. So g of 0, like that's going to be 1. I'll put it right there, and g of 1 equals 0. Okay, I don't know what it's doing, but it could do something like that. It could do like some sort of curve thing. It could like just come up and down, and then and there. All we know is that the function is continuous, so it cannot do something like that because that would not be continuous. Keep that in mind. Which of the following is not necessarily true? So let's just go through these one by one. There exists a number h in 0 to 1 such that g of h is greater than or equal to g of x for all x in 0 to 1. So for every possible value in 0 to 1, so h is going to be in between 0 to 1. So here's 0, there's 1. And we're saying h is somewhere in between there, and that the function has to be greater than or equivalent to g of x at some point. Well, since the function's continuous, if I say, all right, h is there, that there exists a number h, and that this is the same function, yeah, it has to be greater than or equal to every value in between. Then if I change it up, if I say h is down here, then yeah, it has to be this point. I mean, it's not greater than at every point, but it was equal to at one point in there. Now, as we're going through that one, so we know A is going to be good. All right, so A is good. Sorry for that check. All right, so we know A is good. For all A and B in 0 to 1, if A is equal to B, then G of A is equal to G of B. So really what we're saying is if A is equal to B, then this has to be true. So then really this is kind of like not even a real question. G of A, if A is B, then it has to be G of B. I can't even think of another, G of A, because that would be equivalent. Of course they're going to be the same value. I can't even think of an example where that would not be true unless this was not a function and it was a relation. Moving on to C, there exists a number h in 0 to 1 such that g of h equals 1/2. All right, so g of h equals 1/2. So here we're going to 0. We also know that g of 0 is 1, so that's the height, and that we have 1 comma 0, so that's the height there. So we know in between 1 and 0 has to cross 1/2. It'll have to do that. At some point, it'll have to do that. So that has to happen. So that is also true. To D, there exists a number h in 0 to 1 such that g of h equals 3/2. So again, we'll put an h somewhere. And then 3/2 we'll put right there. So, all right, is that necessarily true? Well, we don't know that the function goes up and then comes back down. We don't know that. There's nothing in the prompt that tells us that's true. This function could just go like that, in which case it'll never reach that 3/2. So this one, the answer would be D, because that's not necessarily true. Moving on to 3, if a function f is continuous for all x, and if f has a relative maximum at -1 to 4 and a relative minimum at 3, -2, which of the following statements must be true? Okay, so let me put a relative maximum at -1, 4. So we'll just put a point here like we did on the last problem. And then 3, -2. So let me see. Let me just put this in a grid. So that we'll just kind of say, all right, that's -1 comma 4. And then 3, -2. All right, so then, sure. Doesn't have to be perfect. Just what I'm thinking about in my mind. And it has to be true. All right, so we also know that this is continuous. Again, like the last problem, I don't know how it's continuous, but we do know it's going to go do something like that, or it'll do something like that. We don't know. All we know is that it has to get from point A to point B. All right, so the graph of f has a horizontal asymptote. Well, looking at what I just drew, is that something that has to be true? Well, it doesn't have to be true, because what I just drew right here does not have a horizontal asymptote, and it goes through those 2 points, and it's continuous. So that's not going to be true for us. The graph of f has a horizontal tangent line. All right, so a horizontal tangent line at 3. So what we're saying here, relative minimum at 3, -2. So it has to have a horizontal tangent line that does something like that. So really what we're saying is, all right, it'll just touch it and then it'll go do other stuff right after that. But from the information that we're given, we don't necessarily know that that is happening. All we know is that this is a relative minimum for all the x value. Now we're just going to, we can't assume that the domain is -infinity and +infinity, all real numbers. It could just stop again right here, in which case this does not necessarily have to have that horizontal tangent line. You need to have it on both sides for it to have that horizontal tangent line. So that one is also not necessarily true. But as we've been going through everything, we have been seeing that everything that we've been sketching, whether it came like that, whether it came like that, all of the things we've been sketching has intersected both axes. No matter what we did with what we drew, the function would always have to go through both axes, no matter what. So that one is going to be our answer. All right, here we are, number 4. If the limit of f of x as x approaches 3 is equal to 7, again, which of the following must be true? All right, so we know here at 7, let me just draw kind of like a horizontal line, say 7's there. And then as we're approaching, actually, no, let me draw this like this. So like, as we're approaching 7, we'll say 7's right there, that the limit is equal to 7. So do we know that? Actually, look at what I just drew, because from this piece of information, I didn't know that this was filled in. So as I'm going through these options, it says f is continuous at x equal to 3. Well, what I just sketched, is that continuous? No, we have a removable discontinuity. We would need to know that this is filled in. but from the information given, we don't know that that's happening. And we also don't know, as I just said, that f of 3 equals 7. That's the missing piece that's disconnecting these two. So we know that that's also not necessarily true. It says must be true. It could, but we don't know. So neither one of those options are true. So the answer here is A, none. Moving on to question 5. If f of x is equal to natural log x from 0 to 2, and it is equal to x squared natural log 2 from 2 to 4, then the limit of f of x as x approaches 2 is going to be equal to what? The limit as x approaches 2, remember, we're going to be needing it from the left side and the right side. So from the left side, we'll be using this first equation, and then from the right side, we'll be using the second equation. So let's figure out what both of those are equal to. All right, and that is going to give us natural log of 2. I'm not going to really spend any time evaluating it. That's just going to be what I leave it as. And now here we're going to substitute in limit of f of x as x approaches 2 from the right. That's going to be our second equation, so that's going to be 2 squared natural log 2. And that's going to simplify to 4 log 2. 4 log 2 is not equivalent to natural log 2. The function, or sorry, the limit of f of x as x approaches 2 does not exist, because the left hand and the right hand limit are not the same. Moving here, question 6, we just have a simple limit input analysis. So the limit as x approaches 0 of our rational expression here. So always check, all right, so if I get 0, I'm going to do 0 plus 0 over 0 minus 0, and we're getting that indeterminate form, 0 over 0. So that means we have to do more work, and what I notice is that I can factor out an x squared in that numerator. So we're going to have 5x squared plus 8, and then in my denominator, factor out an x squared. So we're going to have x squared and 3x squared minus 16. And let's see what we get for this. Well, those x squareds, those divide out, and now we have 5x squared plus 8 over 3x squared minus 16. Now, if I substitute 0 in, we're going to get 0 plus 8 over 0 minus 16. And we can simplify this, 8 over negative 16. That is equal to negative 1/2. So that is what the limit is equal to. Factor and divide out. Looking here at question 7, we're looking at a limit as x approaches infinity. When x is approaching infinity, you're looking at your expressions in the numerator and denominator. And what I notice here is that the exponents are the exact same. So when the exponents are the same, the coefficients are what we're going to be looking at. So 3 over 1, or 3, is going to be our limit as x approaches infinity. What we mean is that this graph actually has a horizontal asymptote. Looking at number 8, if the function f is continuous for all real numbers, and if f of x equals x squared minus 4 on x plus 2, when x does not equal negative 2, then what is the function when x is negative 2? Basically what we're asking is, all right, x cannot be negative 2, and if you're looking here, it's because in the denominator you're getting 0. So we want to say, all right, there's some sort of hole happening. Where do we need to fill in that hole? What I notice in this numerator is I can factor x squared minus 4. It's a difference of squares. So we can have x plus 2 times x minus 2 all over x plus 2. Those divide out, and I'm left with x minus 2. And if I want to figure out what this new f of negative 2 is going to have to equal, well, all I have to do is substitute into this leftover expression. So negative 2 minus 2, that gets me negative 4. So we know that f of negative 2 has to be negative 4. The reason we're saying it's negative 4 is because of this part right here. This function is continuous. So since it's continuous, it has this hole when x is equal to negative 2. We're going to fill in that hole at negative 4. Moving on to question 9. If the limit of f of x is x approaches a equals L, where L is a real number, which of the following must be true? All right, so kind of want to sketch this out. I don't know what it looks like, but I'm just going to kind of sketch something out. So something that we have, so I'll put L right here, I'll put A in a second, and we don't know what it looks like. That's pretty close. And then we'll put A right there. So which of the following must be true? From what I sketched out, we know it's not continuous, or it doesn't have to be continuous because we don't know that the function is equal to L at A. So we're going to take this out. There. So which of the following must be true? From what I sketched out, we know it's not continuous, or it doesn't have to be continuous because we don't know that the function is equal to L at A. So we're going to take this out. All right, and now we want to look at this option B. F of x is defined at x equal A. Well, we don't know it's defined anywhere. We don't know it's defined here. We don't know if it's defined at this point. We don't know if it's defined down here. We just don't know that information from what was given. So we don't know that that must be true. And then this piece, f of a equals L. Well, here's f of a. We, again, don't know that that's true. In fact, if it were true, then this first part would have been true. And since that wasn't true, we know that this also doesn't work. So none of these are going to be correct here. Moving on to question 10, we have a piecewise function given to us. We know that we have this kind of rational expression here when x does not equal 2, so everywhere else. And then we have it equal to 1 when x is equal to 2. So let f be the function defined above. Which of the following statements about f are true? F has a limit at x equal 2. So what we want to see, does the left hand limit, does that equal the right hand limit? So let's figure that out real quick. Let's see if that one is true. So the left hand limit is going to be, well, let's see. We can just use this first equation. So let's see, let's write this out. X squared minus 4 over x minus 2. All right. And then we could factor the numerator x plus 2, x minus 2. Difference of squares on x minus 2. Those are going to divide out. And since nothing weird is happening when x is equal to 2 other than these being divided out, then yes, a limit does exist. Now, if we want to see if the function is continuous at 2, we need to see, does the limit and the function equal the same value at 2? So we know that f of 2 is going to equal 1 because this is what it has to equal when x is equal to 2. And I want to come back to this piece and I want to evaluate the limit. So the limit of f of x, let me actually put this in the front. The limit of f of x as x approaches 2. Well, then we divide it out, okay, and then from there we're going to substitute 2 in, so 2 plus 2, we're going to get 4. So basically what we see is that the limits are approaching 4, but the function's value at 2 is actually equal to 1. So is that continuous? No, that is not continuous. So what is true is just 1 only, A. All right, moving on here to question 11. Let f be the function defined above. For what value of k is f continuous at x equal 2? So we want to make this function continuous. So let's actually look here. The first thing I noticed about 2x plus 1 times x minus 2 on x minus 2 is that those pieces are dividing out. If we want to find the limit of f of x as x approaches 2, well, all we have to do now is substitute 2 into 2x plus 1. So 2 times 2 plus 1, we're going to get 5. And then all we need to say is, all right, we need to make the function at 2 equal to 5. Well, how are we going to say that? Well, 5 is going to be the value for k. So we know that for what value of k makes this function continuous? Well, k is equal to 5. Moving on here to question 12, we have another limit as x approaches infinity. But it's a bunch of stuff that has to get multiplied out. What's nice about these is look for what's going to get you the highest powers. So if I were to kind of distribute here, 2x times 3, I get 6x. But 2x times negative x, I get negative 2x squared. I don't care about anything else now because that's going to be the highest power in the numerator. And then in my denominator, I'll be making x times x, and if no matter what else I'll multiply, I'm not going to get a higher power. So we're going to have x squared. Now, since we're doing the limit as x approaches infinity, well, again, these have the exact same power. So we're looking at the coefficients, -2/1, which is just equal to -2, and that would be the limit. On to question 13. The graph of which of the following equations has y equal to 1 as an asymptote? So y equal to 1 is this horizontal line. That's what we'd be looking at. So natural log x does not have that asymptote. In fact, it actually does one of these. So it doesn't even have that asymptote going through there. So that can't be our answer. In B, we have this. So we're kind of going to be looking at the horizontal asymptote as x approaches infinity or negative infinity. So let's see this, the limit as x approaches infinity. Well, if we're looking at this, we're looking at the coefficients, and then we're going to get 1/1, which is 1. So this one does have it, but I do want to look at these other answers. So this one, y equals x squared over x minus 1, the numerator has a higher power than the denominator. So this one is actually going to infinity. This one is not going to approach a single value because the exponents are different. And then e to the negative x, you're going to want to rewrite that 1 over e to the x. And when you get this, you're going to be getting the limit as x approaches infinity, a really large number in your denominator. So this is actually going to approach 0, not 1. All right, on to question 14. For x is greater than or equal to 0, the horizontal line y equal to 2 is an asymptote for the graph of the function f. Which of the following statements must be true? So the horizontal line y equal to 2 is an asymptote for the graph of the function f. All right, and for x is greater than or equal to 0. So here is y equal to 2, and the graph of the is an asymptote for the graph of the function. So it could do something like that, or a function could do something like that. We don't know but we do know that it has that kind of asymptote. So it could be like any of those. We don't know. All right, do we know that f of 0 equals 2? No, what I just sketched, we don't know that that's happening. It could be happening, but we don't know that that's actually happening. So we're not going to accept that as an answer because we don't know that it must be true. F of 2 is undefined. So here's 2. Do we know that it's undefined right there? Well, we don't really know that that's undefined because we just sketched something that has it. And the only piece of information is that we have this horizontal asymptote. So we don't know that that's not going to be undefined there. The limit of f of x as x approaches 2 is infinity. Well, be careful with this one because this looks right, but really what this is saying is at x equal to 2, it's going up to infinity. And that's not what we're saying. We want a horizontal line y equal to 2. But this one is correct. The limit as x approaches infinity of f of x is going to 2. That's the one we're looking for. 14's answer is D. And lastly, if the graph of y equal to ax plus b over x plus c has a horizontal asymptote y equal to 2 and a vertical asymptote at x equal to -3, then a plus c is equal to what? Okay, so let's take this horizontal asymptote first. When we're looking at horizontal asymptotes, we're looking limits of our function as x approaches infinity or negative infinity. So we're looking at these exponents. These exponents are the exact same. All right, we also know that this coefficient is 1. So a over 1 must be 2 because we're saying this horizontal asymptote is 2. So what is a? Well, a now has to be 2. 2 divided by 1 gives us 2. And then we also have a vertical asymptote x equal to -3. So we know that x plus c is going to get a 0. That's where we're getting vertical asymptotes. And since we're saying x is equal to -3, we're going to say -3 plus c is equal to 0. Well, we just need to solve for c, so c is going to equal 3. Now we just need to come back and answer our question. What is A plus C? Right? I guarantee you, as you're going through multiple choice, 2 and 3 are going to pop up. And then you're going to answer one of those, and it's not going to be correct, so you need to add them. 2 plus 3, our answer is going to be 5. So that completes the multiple choice video. I will be coming out with another video on the 2 free response questions that are at the end of this review. But if you have any questions on these multiple choice questions, you just let me know. My name is Mr. Hernandez, and I'm always here to help.